Hey everyone! In this video, we're going to learn about apparent weight. We'll talk about what apparent weight feels like conceptually, and then we'll cover it in more detail. After that, we'll explain the difference between weight and apparent weight. And we'll calculate the apparent weight of a person in an elevator for 5 different scenarios. In the last scenario, we'll talk about weightlessness and how a person or any object can have 0 apparent weight. We already learned that an object's weight is the gravitational force, Fg, acting on the object from the Earth. We always use this equation to calculate the weight, which is the object's mass multiplied by g, the acceleration due to gravity, or the strength of the gravitational field. So if you have a mass of 80 kilograms, then your weight, the gravitational force, is 80 kilograms times 9.8 meters per second squared, which is 784 newtons. And a scale is often used to measure the weight of an object. So if you stand on a scale on the ground, the scale would read 784 newtons, or 176 pounds. That is your actual weight. But in some situations, like if you're riding on a roller coaster, you might feel like your weight is changing at different points in the ride. When you go through the bottom of a curve, you actually feel heavier. When you go over the top of a curve, you feel lighter. And if you're on a flat part of the ride, your weight would feel normal. Your actual weight, the gravitational force, is not changing. The thing that is changing is what we call your apparent weight. When you feel heavier at the bottom of a curve and you feel like you're being pushed down into your seat, your apparent weight is greater than your actual weight. And when you feel lighter at the top of a curve and you feel like you're lifting out of your seat, your apparent weight is less than your actual weight. But when you're on a flat part of the track and you're not moving up or down, your apparent weight is the same as your actual weight. So it seems like your apparent weight might be affected by your motion. Here's another scenario. The International Space Station is in orbit around the Earth. The astronauts in the space station have 0 apparent weight, which we refer to as weightlessness. So they feel like there's no gravity, and they can float around inside the space station. You might think this is because there's no gravity in space, but we learned in the last few videos that the strength of the Earth's gravitational field at the height of the space station is still 8.7 meters per second squared, almost 90% of the gravity that we feel on the ground. So why do astronauts feel weightless? We'll come back to that later. A simpler and more common scenario would be a person riding in an elevator. Let's say it's moving upwards. When the elevator is speeding up, you would actually feel heavier. When you're moving at a constant speed for most of the ride, you would feel normal. And when the elevator is slowing down, you would feel lighter. But what's causing you to feel heavier and lighter? Is something physically happening, or is it just an illusion? Well, if you were standing on a scale in the elevator, you would actually see the number on the scale change. The number would be bigger when you're speeding up, and it would be smaller when you're slowing down. So it turns out that a scale does not measure your actual weight, it measures your apparent weight, and your apparent weight is changing. Your actual weight is always the same, m times g, which is 784 newtons. And when you're moving at a constant speed for most of the ride, your apparent weight is the same as your actual weight. But when you're speeding up and slowing down, your apparent weight changes. So what's causing you to feel heavier or lighter? Gravity is the same in each case, and the only other force that's acting on you is a force from the floor pushing upwards against your feet, and we call that a normal force. That's the force that you feel, and that's what's changing. So an object's apparent weight is the normal force, Fn, acting upwards on the object. For example, this 10 kilogram box is sitting on the ground. There's a downwards gravitational force from the Earth, which we call the weight, and there's an upwards normal force because the box is in contact with the ground. That normal force is the apparent weight of the box. This is just a label for the normal force, and in this case, the apparent weight is equal to the actual weight, 98 newtons. Apparent weight can also refer to other supporting forces like tension from a rope. Here, the box is hanging from a rope, and there's no normal force, so the apparent weight might refer to this upwards tension force. But most of the time, apparent weight means the normal force, and a question will probably tell you if it means something else. We learned in another video that a scale measures the normal force on an object, and the apparent weight is the normal force, so a scale measures an object's apparent weight, not its weight or its actual weight. Or if we attached a hanging scale to this rope, the scale would measure the tension force in the rope, which would tell us the apparent weight of the box. So why do we usually think that a scale measures an object's weight? Let's review the difference between weight and apparent weight, and then we'll see when they're equal and when they're different. Weight is the gravitational force on an object, Fg, and apparent weight is the normal force on an object, Fn. Or, like we said, it could be another force like tension. An object's weight depends on its mass, m, and the gravitational field strength, g, which is also the acceleration due to gravity, but it does not depend on the object's motion or other forces. And we assume an object's weight is constant near the surface of the Earth, because we assume g is constant. An object's apparent weight depends on the other forces acting on the object, and it depends on the motion of the object, which we'll see in a minute. An object's weight can be determined using this equation, and it's always equal to mg. An object's apparent weight can be determined using a scale, like we just mentioned, or by drawing a free body diagram and using Newton's second law, usually in the y direction. And finally, an object's apparent weight will be equal to its actual weight if the object is not accelerating up or down, and ay is 0. This is true if the object is sitting at rest, like this box, or if it's moving at a constant speed. Let's explore that last point and walk through some examples of finding a person's apparent weight in an elevator. In this first scenario, the elevator is not moving, so its velocity is 0 and its acceleration is 0. If we draw a free body diagram of the person, there's a downwards gravitational force, which is the weight, and an upwards normal force from the floor, which is the apparent weight. And let's say up is the positive y direction. We can find the weight using the weight equation, but to find the apparent weight, we need to use Newton's second law in the y direction. The net force is the normal force minus the weight force, because we said up is positive. We plug in 80 kilograms for the mass of the person, and 0 meters per second squared for their acceleration. The right side of this equation just becomes 0, which means the normal force is equal to the weight force. We can replace the weight force with mg, and plug in 80 kilograms for the mass, and 9.8 meters per second squared for g. That gives us 784 newtons for the normal force acting on the person, and that is their apparent weight. If we have the person stand on a scale in the elevator, the scale would measure the apparent weight. But notice that in this case, the person's apparent weight is equal to their actual weight, and they would feel normal, like they're standing on the ground. That's because the person is not accelerating up or down, so the net force on the person must be 0. These are the only two vertical forces on the person, so they must be equal to each other. In the next scenario, the elevator is moving upwards with a constant velocity of 2 meters per second. But it's not accelerating, so a is still 0. That means that the forces and the equation for Newton's second law is the same as the last scenario. Remember that forces are related to an object's acceleration, not the velocity. So it doesn't matter that this elevator is moving at a velocity of 2 meters per second. The person's apparent weight is still equal to their weight. The elevator could also be moving downwards at 2 meters per second, or even 100 meters per second. As long as the velocity is constant, so the acceleration is 0, their apparent weight is equal to their actual weight. If you were in this elevator, moving at a constant velocity of 100 meters per second, you wouldn't actually be able to tell that you're moving, except for maybe some noise and vibrations. You would feel the elevator accelerate and get up to that speed, but once you're moving at a constant velocity, it would feel the same as the elevator that's not moving. So what if there is acceleration? In the next scenario, let's say the elevator is accelerating upwards at 1 meter per second squared. Now, when we write out Newton's second law, we would plug in positive 1 meter per second squared for the acceleration, because we said up is the positive y direction. The right side of the equation simplifies to 80 newtons, not 0, so now the normal force is equal to the weight force plus 80 newtons. If we replace the weight with mg and plug in those values, we get 864 newtons for the normal force and the apparent weight. So now, the apparent weight is greater than the actual weight. The person is accelerating upwards, so the net force must be upwards, so the normal force must be greater than the weight force. And remember that acceleration is a change in velocity, which is a vector. This elevator could be moving upwards and speeding up, or it could be moving downwards and slowing down. The acceleration is upwards in both cases. So if you're in an elevator, you would feel heavier anytime it's accelerating upwards, either at the beginning or the end of the ride. What if the elevator was accelerating downwards at 1 meter per second squared? Now, we would plug in -1 for A, because we said down is the negative y direction. This means that the normal force is equal to the weight force minus 80 newtons. That's going to give us 704 newtons for the normal force. So when the person is accelerating downwards, the net force is downwards, so their apparent weight is less than their actual weight, and they feel lighter. Again, this could happen at the beginning or the end of the ride, depending on whether you're going up or down. Finally, what would be the person's apparent weight if the elevator was accelerating downwards at 9.8 meters per second squared? We would plug that value in for A in Newton's second law. When we solve for the normal force, we get 0 newtons. So there's actually no normal force acting on this person, and they have 0 apparent weight, which we refer to as weightlessness. Their actual weight is still 784 newtons, but their apparent weight is 0. This might seem weird at first, but we know that 9.8 meters per second squared is the acceleration due to gravity. So if the elevator and the person are both accelerating downwards at that rate, then they're just falling. Or we could say they're in free fall. This would be like dropping the elevator at some height above the ground. And the person's motion would be the same even without the elevator. All objects in free fall accelerate downwards at 9.8 meters per second squared, so the elevator, the person, and the scale all accelerate together, so there are no normal forces or contact forces between them, and the scale would read 0 newtons. The only force acting on the person is the gravitational force, so they feel weightless. But this is only true if their acceleration is equal to g. So to recap, an object's apparent weight is the normal force acting on it, so it depends on the vertical acceleration of the object. If the acceleration is 0, the apparent weight is equal to the actual weight, even if it's moving at some constant velocity up or down. If the object is accelerating upwards, the apparent weight must be greater. And if it's accelerating downwards, the apparent weight must be smaller. And if an object is accelerating downwards at g, 9.8 meters per second squared, the object is in free fall, so it has no normal force, no apparent weight, and we say the object is experiencing weightlessness. So now that we know more about apparent weight, why do you feel heavier and lighter at different points on a roller coaster? We're going to learn more about this in the lesson on centripetal force. But basically, When you're going around a curve, your net force and acceleration point towards the center of the curve. So when you're at the bottom of a curve, the acceleration and the net force is upwards, so the normal force is greater than the weight force, and your apparent weight is greater than your actual weight, and you feel heavier. At the top of a curve, the acceleration and net force is downwards, so the normal force is less than the weight force, and your apparent weight is less than your actual weight, so you feel lighter. And if you're not accelerating up or down, your apparent weight is equal to your actual weight, and you feel normal. And finally, why do astronauts feel weightless, and how can they float around inside the space station? The value of g at the height of the space station is 8.7 meters per second squared. So there's still plenty of gravity, and each person's actual weight is still about 90% of their weight on the ground. But we just learned that a person has zero apparent weight when they're in free fall, when they're accelerating towards the Earth at the same rate as g. So the astronauts feel weightless because the space station and the astronauts are actually in free fall. The only force acting on them is the gravitational force, so they accelerate towards the Earth at 8.7 meters per second squared, the value of g at that height. Another way to think about this is that a person in the space station is basically the same as a person in a falling elevator. The astronauts and the space station are both falling at the same rate, so the astronauts have zero apparent weight, and they can move around the space station as it falls. If they had scales in the space station, they would also float around, and they wouldn't be very useful. So the space station is in free fall, and it's accelerating towards the Earth at 8.7 meters per second squared. But obviously, it doesn't just fall and crash into the Earth. That's because it's also moving sideways extremely fast, over 7,000 meters per second, so it never hits the Earth, and we say it's in orbit. Its own inertia keeps it from falling straight down, and we'll learn more about that in the lesson on orbital motion. But orbital motion is technically the same as projectile motion. The space station may be moving sideways at a constant speed, but its acceleration is always towards the Earth at the same rate as g. So there's still gravity in space, but the astronauts are in free fall, so they have no apparent weight. Alright, that's it for this video. Thanks for watching, and I'll see you in the next one.